So when we looked at our exponential graphs, when we had a base that was greater than 1, we see that we have an increasing curve from left to right. And so we get a graph that approaches the x-axis, and then we get exponential growth, increasingly fast. If we were to take all those points and find and plot the inverse of those points, we get a graph that instead approaches the y-axis and then increases very, very, very slowly over time, but still increases as we go to the right. We call that a logarithmic function. Okay? A logarithm. It's the inverse of an exponential. So logarithms were first developed as kind of a way to represent and evaluate really, really large exponential numbers, or also some that have a very, very small exponential number. Lots and lots of zeros involved. Okay? So it was a way to represent and show those on a shorter scale. They have very similar properties to that of exponential functions. The base cannot be 1 and it cannot be negative, so our base has to be greater than 0. It cannot equal 1. Okay? The base of the logarithm is the part b, that little number that shows up right there next to the logarithm. That's the base. And then we have the value x. That is called our argument. And the way that a logarithm works is it says that how many times do I need to multiply the base by itself in order to get my argument? And that's what a logarithm ends up evaluating to. Because of that one-to-one relationship and that inverse relationship from a logarithm and an exponential, we can rewrite logarithms in an exponential notation, which allows us to evaluate certain exponential functions using logarithms, as well as be able to evaluate logarithms using exponential notation. And so we need to be comfortable going back. They're going to have their own special uses in order to evaluate. So converting is really straightforward. It's a pretty simple process. I like to use what's called the spiral method. The base of a logarithm and the base of its equivalent exponential function will always be the same. So we start at the base. Okay? We start at the base. So the base of the logarithm is going to be the base of my exponential function. And then what we do is we say, okay, well, I'm going to draw a line from the base to the other side of the equal sign. And what this says is I'm going to have base b to the power of y. Okay? So base b to the power of y, and then we come back around on our spiral equals x equals x. And that's how we get a logarithm into exponential notation. And we'll do the same thing to go from exponential notation to a logarithm. So base b to the power of y equals x. That gives me b to the y equals x. To go exponential to logarithm, we're going to do the same idea. We're going to start at base b. So we're going to say I have a log with base b, a logarithm with base b. So log base b of x, log base b of x. That is our argument now. If you want to put it in the parentheses, you can make it a little bit cleaner. Log base b of x, and then we come back around equals y. Log base b of x equals y. B to the y equals x. And so we can kind of convert back and forth between those. So let's do it with some actual numbers. We want to write each of these in logarithmic notation. So we're going to start with our base of 5. So we have log base 5, and then we're going to go to the other side of the equal sign. Log base 5 of 625 equals 4. And that way that is read is saying that, okay, if I want to multiply 5 by itself a bunch of times, how many times do I need to do it until I get to 625? 4 times. That's what a logarithm evaluates. Okay, how many times do you need to multiply something by itself? Okay, so for B, log base what? Log base 2 of 1 over 8 equals negative 3. Pretty straightforward, right? Log base 2 of 1/8 equals negative 3. For C, log base what? Log base 4 of cube root of 4 equals 1/3. Log base 4 of 15 equals x. Log base pi of equals, there you go. Okay? Pretty straightforward. Now let's do logarithms into exponents. What's the base of my exponent going to be? 4. 4 to the power of 2 equals 16. 8 to the power of equals 1/8. What's my base for C? 3 to the power of equals square root of 3. So 1/2 equals square root of 3. What's the base for D? X to the equals 25. And last one. Good. 6 to the x power equals 206. So converting exponential equations to logarithmic ones, converting logarithmic equations into exponential ones, just follow that spiral pattern. It's going to be pretty. Starting with the base. As long as you got that all around the loop, it's going to be pretty easy. So what we're going to do is use that relationship in order to evaluate, in order to simplify different logarithmic as well as exponential equations. So we look here, and I want to simplify these. I have log base 2 of 32. And what this is asking, how we evaluate it, is saying, well, how many times do I multiply 2 by itself to get 32? That's what it's asking. How many times do I multiply 2 by itself to get 32? Okay, we multiply it by itself 5 times. So that's what that's asking for. Simplify it, it equals 5. But sometimes it's a little easier if we take the expression, we write our own equation, which we can absolutely do. And I can say, all right, well, let's take this expression and let's turn it into an equation. I want to know what it equals. Well, let's just set it equal to x, and we can solve for x. And we can write it in exponential notation. 2 to the power of x equals 32. Now we can use our uniqueness property of b to the x and say, well, let's just take 2 to the x and rewrite 32 as 2 to the 5th power. And then we see that uniqueness where x has to be 5, so our logarithm simplifies to 5. So we can do the same thing here. 5 to what power gives me 1 over 25? Not the second, close. The negative second, because I need to get it reciprocal. Negative 2. We look at 4 to what power equals 2? Say what? 4 to what power equals 2? If we want to do uniqueness, We can rewrite 4 as 2 squared, and then 2 to the first. So 2x has to equal 1. X equals 1/2. Log base 2 of 4. What does that evaluate to? Equals 2. 2 to the x equals 4. 2 squared. And we see that uniqueness. Here we're given logarithmic equations. Sometimes we'll use that exponential notation to solve for what the argument would be or for what the base would be in order to make the equation true. So we'll have to rewrite these in exponential form. So log base 6 of x to the equal log base 6 of x equals 2 is what in exponential notation? Squared equals x. And so what does 6 squared equal? 36. So x equals 36. What is b in exponential notation? And how do we solve for x? We could use uniqueness. What else could we do? I think you said it. Fourth root. Okay. So we could do uniqueness. Sometimes we can't do uniqueness, but if I've got it to a 4th power, I can just do the 4th root or the 5th root or whatever it is that I need, and I get 3. Now, note, normally when we 4th root something, any even root, we have positive and negative. Okay? But because the base of a logarithm cannot be negative, we don't have to worry about the negative. It has to be positive. It has to be non-zero positive. Okay? What's exponential notation for c? 3 to the x equals 1. What does x have to be for that to be true? 0. X has to be 0. And then what's exponential notation for d? d to the x equals 1. What does x have to equal in order for that to be true? 0. Because it does not matter what the base is. If the logarithm's argument is 1, the only way to get that to happen is if it equals 0. So whenever, this is actually one of our properties, whenever we have an argument of any logarithm that equals 1, the logarithm has to equal 0. If the argument is 1, the logarithm has to equal 0. So let's look at our properties then. Okay, so we saw that one. Any logarithm with an argument of 1 has to equal 0. That's our first property. Okay? The next property we have is that if I have a logarithm with a base, and then my argument is an exponential that has the same base, then the exponent, the value of the exponent, is the value of the logarithm. Okay? And if we use our conversion and convert this logarithm in exponential notation, we can see why that happens. I take my base, and I raise it to the power of x, and it equals my argument. So x has to equal x. They have to be the same. If I have an exponential raised to a logarithm where the base of the logarithm is the same as the base of the exponent, then the argument will be equivalent to what the exponential function equals. Because again, I can take this conversion and say I have log base b of x has to equal this exponent, which is log base b of x. They have to be equivalent. And so when we look at example A, is that my first property, my second property, or my third property? Which one does that look like? The second property, right? The second property, where I have a logarithm with a base, and then my argument is an exponential with the same base to the 6th power. So what does this have to evaluate to? 6. It has to evaluate to the same thing. If we wanted to work it out, we could just do a conversion. Write it as an equation, and then we solve. 4 to the x power has to equal 4 to the 6. We see the uniqueness. It evaluates to 6. What property do we have for B? The last one. That's our third property. 7 to the power of log base 7 of negative 3 has to evaluate to negative 3. Again, we could write an equation and evaluate it on our own and check log base 7 of x equals log base 7 of negative 3. Since we have two logarithms with the same base, the arguments must be equivalent. So x will end up being negative 3. And then c, we've seen two examples of that already. Any logarithm with an argument of 1 has to equal 0. Okay? Last thing we're going to talk about is graphing our logarithmic functions. Logarithms and exponentials, very, very closely related. We see we're going back and forth and we're using both of them. We will continue to do that while we graph a logarithm. We're actually going to use the exponential notation and kind of graph it in reverse. That's what we're going to do. So if x is a positive real number, b is a constant, b can't equal 1, we have a logarithmic function. Yay, logarithm. The domain is going to be all positive real numbers, and the range will be all real numbers. We want to graph and find the ordered pairs for its inverse. And that's going to make our whole life a lot easier. We can take our function, y equals log base 2 of x, and we're going to write it in exponential notation. Y equals log base 2 of x. Exponential notation. What's that going to be? 2 to the x equals, 2 to the y. 2 to the y equals x. Take it, and we convert it into exponential notation. Those ordered pairs are going to be a lot easier to solve for. But instead of plugging in values for x, we're going to do it backwards. We're going to plug in values for y. So we'll start with our xy chart. What values should we use to plug in when we're solving for our graph? 0, 1, 2, negative 1, negative 2. Tried and true. Okay? But we're going to plug it in for y instead. It's going to be a lot easier to evaluate that way. So we're going to solve for x. 2 to the 0. What's 2 to the 0 equal? 1. So we're solving for our x value. We're just doing it backwards. 2 to the first equals 2. We're solving for the x value. Okay? 2 to the second, solving for the x value. 2 to the negative first, that's our x value, and 2 to the negative second. Thank you. So now we've found our ordered pairs. We just plugged in y instead of x to get the x instead of the y. We did the inverse. We flipped it. And so we can graph the point 1, 0, 2, 1, 4, 2, and then we can also graph 1/2 negative 1, 1/4 negative 2. Now our exponential equation approached the x-axis. Our logarithmic equation is approaching the y-axis instead. And it continues and goes up and to the right. Now, when we graphed our exponential equations, what 2 points did we always have? When I had 2 to the x, y equals 2 to the x. That's my exponential equation. Okay? What 2 points do I know are on that graph? Based on what we did last week. And I think you had it before. 0, 1, and 1, 2. Okay? I had those 2 points, right? We also had an asymptote. Our asymptote was the line y equals 0. Because it never touches the x-axis, right? So we had our point 0, 1. We had the point 1, 2. And we add 2, 4, so it just kind of went up like that, right? And so that was our exponential graph, and it approached this horizontal axis of y equals 0. All right? Well, if I take the point 0, 1, what's its inverse? 1, 0. If I take the point 1, 2, what's its inverse? They're inverse functions. So all of the points that are on the curve y equals 2 to the x, their inverses will be on the curve log base 2 of x. And when we are writing the inverse of a function, what are we doing to all of those ordered pairs? What are we changing when we go from a function to its inverse? We're switching y and x, right? So I switch y and x and I get the inverse is 1, 0. I switch y and x and I get the inverse as 2 and 1. I switch y with x and I get its inverse, which is why now we have a vertical asymptote. On the vertical axis, x equals 0. All of those points will switch. Let's do it again with log base 1/2. X and y chart, same thing, 0, 1, 2, -1, -2. What is that in exponential notation? What's it going to be? After the y equals x. Okay? So 1/2 to the 0 power. 1/2 to the first power. 1/2 to the second power. 1/2 to the negative first power. 1/2 to the negative second power. So we've got 0, 1, 1, 0. 1, 1/4, 2, 2, -1, 4, -2. And down and to the right, because our base is a fraction, less than 1. Still approaching the y-axis. Still approaching the y-axis as it goes up and to the left. If we want to look at the inverse, an exponential decay function, that's our exponential decay function, we're still going to have that symmetry across the line y equals x. We still have the symmetry on an exponential decay function as we do with that logarithm. Okay? And again, we have the points, those inverse points. Every exponential has the point 0, 1 and 1 comma its base. Every logarithm will have 1 comma 0 and its base comma 1. Those inverse points. Base, its base comma 1. Okay? 1/2, there's the point 1/2, 1. Base, comma 1. There's the point 2, comma 1. Its base, as well as that point of 1, 0, and then that x asymptote. So when you look at this chart that I have at the bottom that shows all the features of the logarithms, and you compare it to the one we saw last week on all the features of an exponential, you'll see that everything is switched. They are all swapped for x and y, because that's what we did to get the logarithm. We swapped the x and the y. So it's still a one-to-one function. But instead, now we have an x-intercept of 1, 0 instead of a y-intercept of 0, 1. Now we have no y-intercept because of that asymptote instead of having no x-intercept. We swapped x. Our domain is values greater than 0 rather than our range. Our range being greater than 0. Our range is all real numbers compared to the domain being all real numbers. Everything about the graph switched, including those special points. And those 2 points are going to be the bulk of what you need to know about the graph of an exponential equation or a logarithmic equation. Okay? Anything beyond that is going to be much beyond what many of you are going to do as long as you know those 2 points, you'll be pretty set as far as any exponential logarithmic equation goes. All right? Questions, comments, concerns, queries about the lesson? About the lesson.